A handy analytical approximate solution for a heat transfer problem by using a version of Taylor method with boundary conditions. Abstract. This work presents the modified Taylor series method, MTSM, with the purpose to find an approximate solution for the nonlinear problem that describes the steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature. After comparing MTSM approximation with the exact solutions, we will conclude that the proposed solution is besides of handy, accurate, and therefore it follows that the proposed method is potentially an efficient tool for practical applications. Keywords: nonlinear differential equations, boundary value problems, Taylor series, heat problems. Introduction. The objective of this article is to find a handy analytical approximate solution for the boundary value problem of the steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature. 1. See Figure 1. Given the importance of the heat transfer phenomena, both in pure problems as well as in the design and operation of equipment in applications, it is primordial to research for analytical approximate solutions for the equations describing these phenomena. 1, 2, 9, 10. The Taylor series method, TSM, is employed with the purpose to depict a function in a certain open interval 3. This method is based on the successive obtaining of the derivatives of the interest function, in such a way that to obtain a better approximation more terms of the series are required. As a matter of fact, an inconvenient is that the above-mentioned method provides just a local convergence, for which it means that for obtaining a good approximation for a function by using method, MTSM, in order to find an analytical approximate solution for the nonlinear ordinary differential equation that describes the steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature, which is defined on a finite interval with Dirichlet boundary conditions. The importance of nonlinear problems is that many nature phenomena are nonlinear. For this reason, several methods have been proposed in order to find approximate solutions to nonlinear differential equations. Variational approaches 6, 7, 29, 34, 10 method 13, exp function 14, 15, Adam-Eanes decomposition method 16 to 21, parameter expansion 22, homotopy perturbation method 23 to 34, homotopy analysis method 35, and perturbation method 1036-37, among many others. The rest of the paper is as follows. In section 2, we introduce the idea of modified Taylor series method, MTSM. For section 3 we briefly introduce the heat problem to solve. Additionally, section 4 presents the application of MTSM in the search for an approximate solution for nonlinear ordinary differential equation that describes the steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature. Besides, a discussion on the results is presented in section 5. Finally, a brief conclusion is given in section 6. MTSM method. To figure out how MTSM method works, consider a general nonlinear equation in the form 5. TSM, it is required to employ many terms of the Taylor series. For this same reason, the use of TSM for obtaining solutions for nonlinear differential equations has been rather limited. Taylor series method has been employed above all to find solutions to differential equations with initial conditions, because TSM is directly related with them. Following the idea of 5, we will employ a version of TSM useful to solve nonlinear problems with boundary conditions, by calculating some shooting constants, in our case some initial conditions. Therefore, this work presents the modified Taylor series, where n is the order of the differential equation, n a general differential operator, b is a boundary operator, f, x, a known analytical function, is the domain boundary for, and denotes differentiation along the normal drawn outwards from. First, we increase the order of the differential equation. Mathematical description of the phenomenon. The purpose of this article is the search for an analytical approximate solution for the problem, which describes the steady-state one-dimension conduction of heat in a slab with thermal conductivity linearly dependent on the temperature. where K is a constant related to the number of the desired shooting constants, SC. It is possible to express the Taylor series solution for 3 in the following form. The steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature. Since MTSM is expressed in terms of initial conditions for a differential equation, the procedure consisted of expressing the approximate solution in terms of y0. We determined its value requiring that approximate solution. This section presents the application of MTSM in the search for an approximate solution for nonlinear ordinary differential equation that describes the steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature, C, 12, and 13. This work will follow the general idea of MTSM but will employ just one shooting parameter correspondent to initial derivative. From this view to calculate it will be sufficient ensure that the MTSM solution satisfies the right boundary condition y1, 0, besides to exemplify we will work the case of. We will get an approximate solution for the system, 12, and 13, with good precision performing very few effort. From 12, we obtain the following successive derivatives. Satisfies the boundary condition yt, 1, 0. This condition defines an algebraic equation for, whose solution provides the sought analytical approximation solution. Recurrence differential equations. From Table 1, we note that the difference of accuracy between MTSM and perturbation method corresponds scarcely a difference of a.r.e9.315a104. This small difference shows the convenience of employing MTSM given the difference of effort employed for both methods. While PM solved 5 recurrence differential equations, the proposed method required to solve essentially 3 derivatives and an algebraic equation. From above it is very important to emphasize that, it is possible to improve the accuracy of our MTSM approximation keeping more terms in Taylor series expansion. 19. Conclusions. This work presented MTSM method in order to calculate an analytical approximate solution for the problem that describes the steady-state one-dimensional conduction of heat in a slab with thermal conductivity linearly dependent on the temperature. The method basically works calculating derivatives of several orders and expresses the solution of a differential equation in terms of the solution of one or more algebraic equations. The comparison with other methods of the literature show the convenience of employ MTSM as a practical tool with the purpose to obtain accuracy solutions for boundary value problems instead of using other more sophisticated and cumbersome procedures.